Let's begin with question 4.8. So you can see that we have two pistons, and the big one is moving at a velocity of 2 foot per second and an acceleration of 5 foot per second squared. And what is happening is the big cylinder is actually being pushed, causing the smaller one to also move forward. Now, what we are going to do is assume that the fluid is incompressible. So that means that as the big cylinder moves and pushes in a certain volume, the same volume will be pushed out on the small cylinder side. So the first assumption we need to make is assume incompressible fluid. Okay, then the next thing you want to do is select your control volume. So we are going to select the control volume as the area just before the big piston begins and the area just before the small piston begins. And the idea behind doing that is that if you select, so let me draw it here. So I'm going to draw the piston, or the bottle. It's not the prettiest, but you get the idea. And we put the piston here, and we put the piston here. So what I'm going to do is select the control volume using a dotted line, just like this. And it's going to end just before the two pistons. So what's going to happen is as that piston moves inwards, whatever volume of liquid it pushes through enters the control volume, and whatever volume of liquid it pushes out leaves the control volume. And that way the piston does not enter your control volume. So the control volume remains the same size for that snapshot in time. And it will continue to remain that size as the fluid pushes in and pushes out. So once you have selected your control volume, the next thing you want to do is set up your vectors. So I'm going to put down the velocity and normal vectors. So on this control volume, the important thing to remember is that your normal vector always points outwards and away from the control volume. So outwards, away from, and perpendicular to. So we have something pointing outwards. Okay, it's perpendicular and away from the control volume. Okay, so that's perpendicular, and I'm going to label this N1 and put a bar on top to indicate that it's a vector. And we know that the flow of liquid is into the control volume. So I'm going to put V1. Okay, then on the other side, I'm going to label the exit of the control volume. We know that our normal vector must always be perpendicular to and away from the control volume. So this is normal vector 2, and the velocity is exiting in this direction. The fluid is exiting in this direction, so the velocity is also outwards. All right, so we've set up N1, V1, N2, and V2. Let's proceed with the continuity equation. It is the double integral over the control surface of rho V times N dA plus d dt triple integral over the control volume of rho dV, and that is equal to 0. So because we've assumed incompressible fluid, we're actually saying that everything that enters the control volume is everything that leaves the control volume. And by making that assumption, this term goes to 0. Okay, so we only actually need to fill in this. All right, now we can begin by putting in some variables. So the idea is you don't want to start substituting in your values immediately, and the reason you learn to do that is because later on when you start to solve your problems on a computer, it is much easier for the computer to deal with code or variables and then substitute in values as opposed to working with values from the beginning, because a computer will store up to, more than 10 decimal places. So you are putting a lot of strain on the computer by giving it extra decimal places to deal with. So we're going to solve this entire thing symbolically, and as our last step, substitute in values. Okay. The next thing you want to keep in mind is that the question is asking you for acceleration and velocity of this smaller piston. So there are two variables, so we are going to look for two equations. Right now, I only have one, but just keep that in mind as we go through the question. We'll discuss this a bit later. All right, so I'm going to set up rho of the fluid multiplied by vector 1 multiplied by normal 1. Now, if you ever get stuck with the normals, to convert the normal into a number, you simply say cos of the angle between the normal and the velocity. So you can see if I draw the normal like this, or if I draw the velocity vector like this, and I draw the normal like this, then the angle between the velocity and the normal is 180 degrees. So your normal becomes cos of 180 degrees, which is equal to -1. Okay, so we've got rho Vn multiplied by area, and that will be the area of the piston. I'll call that A1. Okay, plus rho again, velocity 2, and this time the angle between the normal and the velocity is 0 degrees. So we're going to put cos of 0 degrees, which you know is equal to +1, multiplied by area 2 is equal to 0. Okay, now we can move things over to the other side and start neatening things up a bit. All right, so I'm going to leave this term on the left-hand side, rho V2 multiplied by cos of 0, which is 1. So I will ignore it and put A2. On this side, when I move it over, cos of 180 degrees is -1. So when I move it to the other side, it becomes +1. So again, I can put rho V1 and A1. And you can immediately see now that the rows cancel, and we are just left with this. Now remember, velocity 2 is on this side, so we want to solve for V2. So V2 is equal to V1 divided by A2 multiplied by A1. And that is equation 1. So you can quickly ask yourself, okay, we don't know V2, we know V1, we know area 1, we know area 2. So we can immediately solve for V2. Remember, the V2 value that you solve for will be determined by the V1 value that you put in. So if we put in the initial velocity of V1, we will get the initial velocity of V2 out. All right, let's continue. Now we actually need a second equation because we need acceleration somewhere in here. The good thing to remember is that velocity, when differentiated with respect to time, gives you acceleration. So let's go ahead and do that over here. So we can say that V2 is equal to V1 multiplied by A1 divided by A2. Okay, move down. Now, let's fill in the equation for velocity. Remember, this is V2 with respect to time and V1 with respect to time. So V2 as a function of time from your equations of motion, V2 is equal to V2 initial plus acceleration of cylinder 2 multiplied by time. I hope that looks familiar. That's Vf equals Vi plus A delta T. That's the equation. I'm going to say equals to V1. V1 is V1 initial plus acceleration 1 multiplied by time multiplied by A1 over A2. All right. Now we can start thinking about what we know and what we don't know. And before we get there, remember we are dealing with acceleration. So we know velocity 2 initially. We know acceleration 2 initially. We know velocity 1 initially from, we know velocity 2 from this equation. We don't know acceleration 2. Sorry. We don't know acceleration 2. We know velocity 1 initially. We know acceleration 1 initially. And then the time factor becomes the problem. What do we sub in for t? So you can see that this approach is not really going to work. Let us try differentiating it. And perhaps if we differentiate, we can remove some things that we don't need. So I'm going to take d dt on this side and d dt on this side. All right? If I differentiate v2 initially, remember that v2 was just a constant, okay? It's actually 2 foot per second, so it's a constant. So if I differentiate a constant, it disappears, all right? And if I take d dt of a2 times t, then anything to the power of 1, if you differentiate, you'll be left with the constant, is equal to, again, if I take d dt of v1 initially, remember that v1 initially is just a constant. Sorry, I keep messing this up. Sorry. v2 initially is just a constant. We don't know what it is. Okay. Now I'm going to try it. Let's try this again. v2 initially will be a constant when we do solve for it up here. All right? And if you differentiate a constant, it disappears. Then, acceleration 2 is also a constant, and it's being multiplied by t. So when we differentiate it, we'll just be left with a2. On the right hand side, v1 is just a constant at 2 frames per second, 2 foot per second. So if you differentiate a constant, it disappears. And again, if you differentiate a constant multiplied by the variable, you are just left with the constant. And that's a1 divided by a2. So we know acceleration 1, we know acceleration area 1, and we know area 2. So you've now got 2 equations, 2 variables to solve for, and that shouldn't be too bad. So let's start substituting in some numbers. All right, so v2 initially is equal to v1 initial multiplied by a1 divided by a2. And the reason I remove the vector from here is because we're dealing with constant values now. So v2 is equal to v1, which is 2 foot per second, multiplied by area 1. So remember, if you're working out area, it's pi over 4 multiplied by diameter 1 squared. But what you'll find is, if I put in the same equation on the bottom, our 2 pi over 4's cancel. All right? So that gives me 2 d1 over d2 squared. And that then becomes 2 multiplied by diameter 1, 4 inches divided by 0.5 inches, which is 8 squared, which is 64 times 2, which is 128 foot per second. All right. For equation 2, acceleration 2 is equal to acceleration 1 initially, multiplied by area 1 divided by area 2. So I'm going to skip the pi over 4 step and go straight to d1 over d2 squared, which is equal to 8 squared. All right. So acceleration 2 is equal to acceleration 1, which is 5 foot per second squared, multiplied by 64. 5 times 6 is 30, 5 times 4 is 20, so we're left with 320 foot per second squared. And that's how you solve the 2 questions. So the most important thing to take away from this question is that when you need a second equation, you can always just differentiate your first equation and you'll end up with a second equation. All right, I hope this helped.